Hello and welcome to section 1.5, Solving Linear Systems. I know you thought you were solving linear systems already, and you were, but section 1.5 focuses specifically on describing those solution sets and taking a little bit deeper dive into what they mean. So we need to start off with a little bit of vocabulary that your book's going to use throughout the rest of the quarter. So first of all, we're going to talk about the difference between a homogeneous system and a non-homogeneous system. So a homogeneous system looks like this, and you can probably guess from looking at it what they mean by homogeneous, but just in case it's not clear. Homogeneous means essentially all the same. So what homogeneous means here, a homogeneous system, just means that all equations are equal to 0. And compare that to a non-homogeneous system like this, and the only difference there is at least one equation is not equal to 0. Notice it doesn't have to be all three not equal to 0. We still have one equation over here that is equal to 0, but non-homogeneous just means they're not all 0. So there's a little bit of vocab. Your book's going to use this pretty frequently, actually, throughout the rest of the quarter. So the more that you can make that instinctive in your brain to say, oh, homogeneous system, and that means all zeros, the better. Okay, so far aside from a little bit of new vocabulary, we don't really have anything new going on here yet. Both of these systems, for solving them, the first thing you would want to do would be to put them into matrix form. And that's just, again, removing the x's and equal signs and just translating that into matrix format. And again, you should be able to look at the matrix and say the one on the left is homogeneous and the one on the right is non-homogeneous. As long as you know that they're augmented matrices, right? That they actually represent a system of equations and not just coefficients. Anyway, and then beyond that, of course, the next thing to do is to actually row reduce and then take a look at the solution. And you can see the first system has a solution of x1 equals 0, x2 equals 0, and x3 equals 0. And by the way, if this is truly a homogeneous system of linear equations, that will always be a solution to a homogeneous system. No matter what the coefficients are, this 2 could be 200 or 2 million. It'd still be the case that if you plugged in 0 for x1, 0 for x2, and 0 for x3, that you would solve the system, all three equations. So that's probably worth jotting down here somewhere. Is just that all homogeneous systems have what they call the trivial solution. Which is all variables, x1, x2, x3, x4, whatever. That will solve every homogeneous system. And oftentimes the question is going to be for us, is there any non-trivial solutions to a homogeneous system? And keep in mind, since the homogeneous system always has the trivial solution, if there's even one more, how many are there? You can't ever have just two solutions to a system of equations. So yeah, it's either just the trivial solution or infinitely many. That's the only two cases for homogeneous systems. Non-homogeneous systems, of course, don't necessarily have the trivial solution. Matter of fact, 0, 0, 0 solves the first equation, but it does not solve the second or third equations. And it turns out there is just one solution for the non-homogeneous system as well, which happens to be this 3, 1, negative 4. You can see 3 plus 1 minus 4 is 0, and it works in the other two equations as well. So let's take, before we go away from this example, let's take a little bit of a graphical look at what's going on with these three. So these happen to be three variables, so they make three-dimensional graphs. If it was just an x and a y, we'd have graphs of lines, or an x1 and x2. But since we've got x, y, and z, or x1, x2, x3, we've got graphs of planes. So let's take a look at those graphs. Desmos is a lot of people's favorite online grapher. Desmos doesn't do a great job with 3D graphing, unfortunately. So this is another graphing website called math3d.org. So far, it's the best one I've found for graphing three-dimensional equations. Okay, so I've got the three equations in here. I've only got one of them graphed right now. So I've got x plus y plus z equals 0. A is set to be a slider, but I've currently got a set to be 0. And b and c are set at 0 as well. So all three equations are equal 0. So we're looking at the graph of the homogeneous system right now. So x plus y plus z looks like a plane. It goes through the origin. I don't know if you can tell that. Look at it edge on. It is going right through 0, 0, 0, 0, right? It's a little bit hard to know where to stop the edges of planes. This one's got some sort of funky hexagon, octagon type thing going on. But anyway, it's a plane that extends infinitely in all directions, and is at like a 45-degree angle, which kind of makes sense. You've got a slope of 1 in all three directions. Okay, but let's go ahead and look at the other one. Negative 2x plus 2y minus 4z also equals 0 at the moment. B is set to 0. So we'll put that one on there as well. And let's go ahead and turn on the third one. Notice graphically, a solution set means where do all three of them intersect. And notice that they do indeed intersect only at the origin. It's the only place that all three planes intersect. And we already knew that was the solution, and the only solution to our system of homogeneous equations was just 0, 0, 0. So let's go ahead and take a look at the non-homogeneous and see how that's related. Let's see, we had 0 and 12 and 7 were the three numbers it was equal to. So I'm going to change my sliders. I'm going to leave a at 0. I'm going to put b, though. From 0, I'm going to move it over to, over to 12, if I can get it on 12. There we go. I don't know if you could tell very well. Here, let me turn the other two graphs off. When I move b and just change what the equation is equal to, it doesn't like tilt the plane in a different direction. The slope doesn't change. Right? All I'm doing is shifting it. And if you think back to pre-calc in your days of just like adding 2 to an equation, all that does is shift it up or down, right? So that's all we're really doing here, is I'm just shifting that plane. Let's see, and let's get it shifted over to the right number, which for us, which was 12. There we go. And A was already at the right spot, still being equal to 0. And C needed to equal, I forgot already, was it 7? Yeah, 7. Okay, so let's turn C back on and slide it over to 7. I can't get it quite to land on 7. Okay. Okay, so you can see there's a different intersection point right about there where all three of those planes meet. We happen to already know what that intersection point is. It was 3, 1, negative 4. A little bit hard to see in 3D, but there's the x-axis, so there's 3, the y-axis 1, and then the z-axis negative 4, drops us down right about to that spot. Okay, so that's how things look graphically in 3 dimensions. And really the main thing I wanted to point out here was, since all I changed was the number on the right hand side of the equal sign, I wasn't changing the slope of any of those 3 planes, which means I'm not going to ever change, just by changing the numbers, I'm not ever going to change it from having one solution to having multiple solutions. Having multiple solutions, infinitely many solutions, means the planes actually lie on top of each other. And if they don't do that in a homogeneous system, they won't do it in the non-homogeneous system that goes with it. Because again, changing those numbers just changes location of planes, but not the tilt of the planes. So a homogeneous system and related non-homogeneous system always have the same number of solutions. Okay, I think that's actually good for this section. We'll unpack a little bit more of this and do a couple examples. Sorry, not for this section, for this video. We'll do a couple more examples in the next video. All right, I'll see you there.